An ideal massless spring is hung from the ceiling, and a pan suspension of total mass m is suspended from the end of the spring. A piece of clay, also of mass m, is then dropped from a height h onto the pan and sticks to it. Express all algebraic answers in terms of the given quantities and fundamental constants. Determine the speed of the clay at the instant it hits the pan. So that's our first question. We need to figure out the speed as soon as this lump of clay hits this pan. So there's this thing called mechanical energy conservation, something like that. And basically, when you hold the clay at a height h above the pan, it has energy in the form of gravitational potential energy, which is given by the mass times the gravitational acceleration, or the weight times the height or the distance it is held above the ground. And when you drop something, this gravitational potential energy is turned into the kinetic energy. And this velocity is the velocity right the instant before it hits the ground. It is when all of the gravitational potential energy gets transformed into kinetic energy from the fall. So we can use this to derive an expression for the speed or velocity of the clay. And both masses actually cancel because this is a big M as well, since the clay has the same mass the instant before it hits it as it did when it was held a height h above. So the masses cancel. You're left with v squared equals 2gh. So the velocity, the expression for the velocity right before impact, is the square root of 2 times the acceleration due to gravity times the height that it was held above the ground. So I'm going to write that here. That's A. Square root is a little too small. So that's the first part. Now, B asks us to determine the speed of the pan just after the clay strikes it. So there's this thing called momentum conservation, which states that the momentum before a collision is equal to the momentum after the collision. And I am including the initial mass and final mass, and sometimes, like in this case, the clay sticks to the pan. So when that mass sticks to another mass, you would have the final mass would be the sum of those two masses, since those two masses are now joined together, and together they would move at a slower velocity because of that. So that is basically momentum conservation. It's saying that the momentum always stays the same. Even after any sorts of collisions, there's always the same amount of momentum before and after. So we can use this to help us calculate the speed of the pan right after it strikes it. So the momentum of the clay is simply big M, which is the clay's mass, capital M, times the square root of 2gh. And this came from this expression here, where the velocity is equal to the square root of 2gh. And that is equal to the total mass after the impact, which is m plus m, since the clay sticks to the pan and they both have a mass of capital M. And then that is going to be multiplied by their final velocity, which is what we're trying to find. So this yields m times the square root of 2gh is equal to 2 times m times the final velocity. So the masses cancel again, and you get that the final velocity is equal to the square root of 2gh divided by 2. Or you can say it's 1/2 times the square root of 2gh. Either way works. They both mean the same. They both mean the same thing. So that is the answer to part B. final velocity is the square root of 2gh divided by 2. So that's part B. Let's get rid of everything. I wrote my answers all slanted there. Now, part C asks, after the collision, the apparatus comes to rest at a distance h over 2 below the current position. So it stops halfway below the position. Determine the spring constant of the attached spring. So, the kinetic energy it has right after impact. So this is 1/2 2mv squared actually. V squared. Yeah, actually I'm going to start with the basic definition. The kinetic energy can be transformed into something else. And in this case, it is stretching the spring. And the energy of a spring is given by 1/2 times k, which is the spring constant, times x squared, where x is the displacement of the string. And in this case, it's how much the spring stretches. So we know that the kinetic energy can be used to change into spring potential energy, which is given by this right here. So we can say that the kinetic energy can be changed into the potential energy due to the stretched string. And now we can plug all of our known values in. We know 1/2 times the mass is 2m, 2 big M's. This is what we had when the clay stuck to the pan. And v squared is actually the final velocity squared from after the impact, which is the square root of 2gh divided by 2 squared. And that is equal to 1/2 times the spring constant times the displacement squared, which is given to us as h over 2. And we're going to square that. So now let's simplify this a bit. So you have that the mass times, let me see, this gh over 2 is equal to 1/2 times the spring constant times h squared divided by 4. These are both 1/2, so you can cancel that out. K times h squared divided by 4 is equal to mgh. So now we multiply by 4 and divide it by h squared. So moving over here, the spring constant is equal to is equal to 4mgh divided by h squared, which is equal to 4mg divided by h. So that's the spring constant that we just calculated. So I'm going to move our final answer here. So the answer to part C is that the spring constant is equal to 4 times the mass times the gravitational acceleration divided by the height that the clay was initially dropped at. And that is how you would solve this problem here.